In this video, we're going to do a couple examples applying the work-kinetic energy theorem. So let's review a few concepts first. The work done by a constant force is given by the dot product of the force and the displacement. So work equals F dot D, where D vector is the displacement caused by the force. So we see two things must enter when work is done. There must be an application of a force, and there must be movement of something by that force. Then the statement of the work-kinetic energy theorem. The net work done by all forces acting on an object or system of objects is equal to the change in the kinetic energy of the object or system. Work is energy transferred to or from an object or system of objects. Energy transferred to the system or object is positive, and energy transferred from is negative. And we define kinetic energy as the energy possessed by a moving body because of its motion. And kinetic energy can be written as 1/2 the mass times the square of the speed, or 1/2 mv squared. So the work-kinetic energy theorem then is the net work done by all forces equals the change in the kinetic energy. Note that we must include the work done by all the forces acting on the body. We can't just pick one. We have to do all of them. All right, now what about lifting in an object? When I lift an object, gravity is still acting on the object. So when I apply the work-kinetic energy theorem to lifting an object, I have to include the work done by me lifting the object, and I also have to include the work done by gravity because the force of gravity is still acting. So the change in kinetic energy then equals the work done by me, that's what the APP subscript means, work by an applied external force, me, plus the work done by gravity. So I have to include both of those forces. So when I lift, I'm doing positive work because my displacement is upward and my force is upward. And so that's positive work. Gravity, the force of gravity acts downward and the displacement is upward. So those two, the force vector and the displacement, are opposite in direction. And so when I do the dot product, I get a negative number. So the work done by gravity is negative. Now, if the object is stationary before and after the lift, then the final kinetic energy and initial kinetic energy are both zero, so the change in kinetic energy is zero. That means the net work is zero. Thus, the work that I do is equal to the negative of the work done by gravity. So two things must happen for work to be done. There must be the application of a force, and something must be moved by that force. So work gives us a way to quantify what happens when we apply a force and succeed in moving something by that force. So looking at this diagram, we see a woman holding a barbell above her head. Well, the work done on the barbell to lift it up in the air is the average force you must apply to lift it times the vertical distance the barbell is lifted. Looking at the photograph here, we see a woman who's lifted a barbell up in the air. The work done on the barbell while lifting it is the average force applied to lift the barbell times the vertical distance the barbell is lifted. Now, what if she holds the bar stationary above the floor? While she's holding the bar stationary, there's no displacement. So no work is done while she's holding it stationary because it's no longer moving and there's no displacement. So then the work is zero. The work is only done while she is lifting it. All right, before we get into this example, I want to ask you to please tap the like button. It's right below the video. Okay, so let's look at an example of the work-kinetic energy theorem. So at a construction site, a crate is lifted by a motor-driven cable. The lift is done in 3 stages, each covering a 10-meter vertical distance. Part A, the initial stationary crate is accelerated from 0 to a speed of 5 meters per second. It is then lifted at a constant speed of 5 meters per second, and then finally it is slowed to zero speed as it reaches the top. How much work is done on the 80 kilogram crate by the force lifting it during each stage? Alright, now here I've drawn a free body diagram of the crate. We only have the two forces in the vertical direction. We have the tension in the cable lifting it upward and the weight of the crate downward. So here's a perfect place to apply the work kinetic energy theorem. Okay, so part A, we're going to start at zero speed, we're at rest, and then accelerate to 5 meters per second. So we have a change in kinetic energy. So we write the work kinetic energy theorem. Work net by all forces equals delta K. Delta K is the change in kinetic energy, and that's always the final minus the initial. So we have two forces doing work. We have the work done by the cable plus the work done by gravity, and then the final kinetic energy we write as 1/2 mv squared, and the initial kinetic energy is 0. And so solving for the work done by the cable, we get that equals the negative of the work done by gravity plus 1/2 mv squared. Now we can plug in the work done by gravity equals negative mgh. Why is the work done by gravity negative mgh? Well, the weight, of course, is mg, and the weight force is downward, and the displacement is upward. So when I do the dot product between the force and the displacement, I get a negative number. I get negative. And we want the negative of that, so that's why we have the negative of the negative mgh, and then plus the 1/2 mv squared. Now I can just plug in the numbers. So the work done by the cable equals the mass, 80 kilograms, times g, 9.8 meters per second squared, times the height, 10 meters, and then the 1/2 I wrote as 0.5, and then the mass again, 80 kilograms, and our final speed is 5 meters per second, and we have to square that. And after I crunch the numbers, we get 8.8 kilojoules. So that's how much work is done in the first stage. All right, now in the second stage, we're lifting at a constant speed of 5 meters per second. Since the speed stays constant, there's no change in the kinetic energy, so delta K is 0. So I have the net work equal to the work done by the cable plus the work done by gravity equals delta K, which is 0. Solving for the work done by the cable, we get the negative of the work done by gravity plus 0, and then the work done by the cable then is the 80 kilograms for the mass, 9.8 meters per second squared for g, and the 10 meters for the height, and we get 7.8 kilojoules. Now finally, for the last stage, we're going to slow from 5 meters per second down to 0 as the crate reaches the top. So again, we have the net work equals the work done by the cable plus the work done by gravity equals the change in the kinetic energy, which of course is final kinetic energy minus initial. Well, the final kinetic energy is 0 because we slow to a stop, and the initial kinetic energy 1/2 mv squared. So it's 0 minus 1/2 mv squared. So then solving for the work done by the cable, we get work done by the cable equals the negative of the work done by gravity minus 1/2 mv squared. The negative of the work done by gravity, of course, is mgh. So we have the 80 kilograms for the mass, 9.8 meters per second squared for g, and 10 meters for the height. And then we minus the 1/2, which is 0.5, the mass, 80 kilograms, and the square, the speed, which is 5 meters per second. And when I crunch those numbers, we get 6.8 kilojoules. Okay, so that solves this problem. We've got all three stages. So you can see how the work kinetic energy theorem was easy to apply and gives us the correct answer. All right, here's another example where we apply the work energy theorem. So in the figure here, we have a crate sitting on a floor, and we're going to ignore friction. We'll do friction in a later video. So we have three forces applied to this crate, and the crate moves to the right by a distance of 2.5 meters over the frictionless floor. The force magnitudes are given as F1, which points to the right, is 6 newtons. F2, which is upward and to the left, is 4 newtons. And F3, which pushes down, is 3 newtons. F2 is angled at 30 degrees above the horizontal. So during the displacement, what is A, the net work done on the crate by these three forces, and B, does the kinetic energy increase or decrease? Now, one other thing I wanted to point out, notice that we don't have the weight downward, nor do we have the normal force upward included in here. Why not? Well, we're given that the crate moves to the right. And remember, work done by a constant force is the force dotted into the displacement. Well, vertical forces dotted into the horizontal displacement give me 0. So remember, the dot product is the magnitude of each vector multiplied together times the cosine of the angle between them. Well, when the forces are perpendicular to each other, the cosine of 90 degrees is 0. So the vertical forces do not do any work. So we don't have to include any vertical forces here. So not even force 3. All right, so remember, when we're finding the net work, we can either find the work done by each force and sum those together, or we can find the net force and then find the work done by the net force. Well, in this case, we're given that the crate is only moving horizontally. So we know the vertical forces don't do any work. So let's just find the net force in the horizontal direction. So the net force in the x direction, or horizontal direction, we have F1 to the right, and then we have the horizontal component of force 2, which is F2 cosine theta. So the net force is F1 minus F2 cosine theta. The vertical component of force 2 is not going to do any work, so we don't need to include that. So now we can find the net force by plugging in the numbers. F1 was 6 newtons minus F2, 4 newtons times cosine of 30 degrees, and I get 2.54 newtons. So it's positive, and that means it's to the right. So the net horizontal force then, 2.54 newtons. Then, to find the work, we have the force times the displacement. So we have the 2.54 newtons times the 2.5 meter displacement gives me a positive 6.34 joules. Now, part B asks, does the kinetic energy increase or decrease? Well, we see that the net work is positive. So that means we're adding energy to the system. Negative work means we're taking energy from the system. Positive work, we're putting energy into the system. And so since the net work is positive, the kinetic energy increases and the crate speeds up. All right, so far we've looked at the work done by a constant force. Now what happens if the force is not constant and varies with position? So, for example, the work done by a spring. A spring force varies with displacement, and this is given by Hooke's law. The spring force as vector is equal to minus k times the displacement. So the greater I displace the spring, either stretching it or compressing it, the stronger the spring force becomes. The constant k is called the spring constant, and it describes the stiffness of the spring. The larger the k, the harder it is to stretch or compress the spring. The negative sign means that the direction of the force is always opposite to the direction of the displacement. So if I pull on a spring and try to stretch it, the spring force is in the opposite direction that I pull. And similarly, if I try to compress a spring by pushing it together, the spring force pushes against me in the opposite direction of the displacement. So that's what the negative sign means. All right, so now we're going to look at how do we find the work done when the force varies with the displacement. All right, so to look at the work done by a spring, we're going to use this situation here shown in the diagram. We have a spring attached to a block, and we're going to make the block particle-like, meaning that all the parts move together. And we're also going to use a frictionless surface. And we're going to assume that the spring is an ideal spring, meaning that it obeys Hooke's law exactly, and that the spring is very light compared to the block, so we can neglect any effects of the mass of the spring. So in the diagram, the zero position is where the spring is completely relaxed. And so if I move the block to the left, I'm compressing the spring, and if we move the block to the right from the zero position, we're stretching the spring. And we're going to make very tiny displacements where the force doesn't change much over the displacement, and then multiply by that displacement to get the work for that tiny displacement, and then sum those all up. So that first equation, we have the work done by the spring, W sub s, equals the sum of the force over that tiny displacement times the displacement, which we write delta x. So we move the spring a tiny little bit, find the work. Move it a tiny little bit more, find the work. Tiny little bit more, move the work, and sum all of those up. Next, to get the exact work then, we take the limit as the displacements, the delta x's, go to 0. We make those displacements smaller and smaller and smaller. And of course, that gives us the integral of the force times dx, where dx is a differential displacement, an infinitely small displacement. And the limits on the integration are summed from initial position to some final position. So now we just plug in for the spring force, which is minus kx. So we have the integral of minus kx dx. The minus k, of course, is a constant, so we pull that out of the integral. And so we just have the integral of x dx. The integral of x dx, of course, is x squared over 2. So I have a minus 1/2 kx squared evaluated between the initial position and final position, which gives us minus 1/2 k times the quantity of x final squared minus x initial squared. Now I carry through the negative sign, and we get the work done by the spring equals 1/2 k initial squared minus 1/2 k x final squared. So that gives us the work done by the spring moving between two positions. Now be careful here. When we normally find the difference between two things, we find like a delta x or a delta k, we always do final minus initial. But here we have the initial minus final. Now suppose we take our initial position to be at x equals 0 when the spring is completely relaxed. Then the work done by the spring is minus 1/2 kx squared. So notice then that the work done by the spring is always negative. And if we think about the situation, that makes sense. If I reach in and I displace the block and just let it go, it's going to oscillate back and forth around the relaxed position, the x equals 0 position. So as the block moves to the left, compressing the spring, it's going to slow down. So the kinetic energy is going to decrease, meaning the work done by the spring is negative. And similarly, when it moves to the right, stretching the spring, it's going to slow down in that direction as well, meaning that the work done by the spring is negative. It's removing kinetic energy from the system. So the negative sign there makes sense for the situation. Okay, so remember, that was the work done by the spring force. Now, what if I reach in and I move the block? Then I am an external force, so my applied force then also does work, and I'm going to write that as W with an A subscript because that's the work done by me, my applied force. And then the spring also does work, and so the work done by the spring force we write as W sub S. So by the work kinetic energy theorem, the change in kinetic energy, which is the final minus the initial, will equal the work done by my applied force plus the work done by the spring force. And if the block is stationary before and after any displacement, then the change in kinetic energy is 0. That means the work done by my applied force will equal the negative of the work done by the spring. Now, caution. If the block is not stationary before and after that displacement, then this, of course, is not true. So be careful of that. All right, let's look at an example problem with a spring. So here we have a 0.25 kilogram stone is dropped onto a vertical spring with a spring constant of K equals 250 newtons per meter. The stone compresses the spring by 0.15 meters before momentarily coming to rest. While the spring is being compressed, what is the work done on the stone by A, the force of gravity, and B, the spring force, and C, what was the speed of the stone when it hit the top of the spring? All right, I have a drawing of the situation here on the right, and this is the stone falling on top of the spring. So the stone will have some kinetic energy when it hits the top of the spring, and then when it compresses the spring, that kinetic energy will then be 0. And we're given how far that spring is compressed. Since we know how far the spring is compressed, we can find the work done by the spring. And we also know the work done by gravity over that distance because we have the mass of the stone and we have the displacement. So this is a good example for applying the work kinetic energy theorem. All right, so first we want to find the work done by gravity. Well, gravity, of course, is acting down, and our displacement is also down, so the work done by gravity is just mg times the displacement y. So the mass is 0.25 kilograms, g, of course, 9.8 meters per second squared, and our displacement is 0.15 meters. When I crunch those numbers, I get 0.3675 joules. I rounded to two significant figures of 0.37 joules. So that's the answer for part A. Now for part B, we want the work done by the spring, and that, of course, is negative 1/2 ky squared because we're compressing the spring in the vertical direction. And so I have a negative 0.5 for the 1/2, 250 newtons per meter for K, and then 0.15 meters for the Y, and we have to square that. And so I get negative 2.8125 joules. Rounding to two significant figures, I get a negative 2.8 joules for the work done by the spring. Notice that the work done by the spring is negative. Well, and of course, the block slows down. So the spring, work done by the spring then, is removing energy from the system. All right, so finally part C, what was the speed of the stone when it hit the top of the spring? Well, we know that the net work equals the change in the kinetic energy. The final kinetic energy, of course, is 0 since it came to rest. And so we can get the speed when it hit the top of the spring from the kinetic energy, 1/2 mv squared. So applying the work-energy theorem, we have the work done by gravity plus the work done by the spring is equal the final kinetic energy 0 minus the initial 1/2 mv squared. And then we can solve for the velocity. So I have 1/2 mv squared equals the negative of the quantity work done by gravity plus the work done by the spring. And then solving for the velocity, I get negative 2 times the quantity work done by gravity plus the work done by spring divided by the mass. And so then I plug in the numbers. The work done by gravity was 0.3675 joules. The work done by the spring was negative 2.8125 joules. And then divide by 0.25 and take the square root, and we get the velocity was 4.4 meters per second. So the speed of the stone when it hit the top of the spring was 4.4 meters per second. Alright, so that's the end of this video. In the next video, I'll do some more examples of work by a general variable force, and then we'll also move on and talk about power and do some examples with power. Power is the rate of doing work. So if you haven't done so already, please tap the like button below the video.
Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel, and please subscribe. I hope you find my videos useful.